Thank you so much. Yes, that's a very kind introduction. And first of all, I want to thank all of the organizers for having a wonderful conference. Really very interesting, fantastic talks up till now. And really, really very honored and nice to be here. And indeed, I started working at a company called Quantinuum, and before that I have been working as a university professor most of my life. And so now I entered into the dark side, as some people say. And Quantinuum really is I have to say a little bit about what Quantinuum does. It is really a full stack quantum computing company that has both hardware and software. And you can see here that it has, so it has sort of, its computer is called H series, and it's full stack. And let me say a little bit about it. Here you see it's based on trapped ions, and here you see the latest in the H series, H2, which has this trap. It has now 32 fully connected qubits with very high single and two-gate fidelity, the best actually in the business. And so here you see it works on these trapped ions, and usually people think of these trapped ions as in a line, but actually at Quantinuum they use a different trap to trap these ions. Here you see this is the newest H2, where these ions sort of run around in a racetrack, and whenever two of these qubits need to do a 2-qubit operation, they actually go together in a gate zone, and then this operation is done. Here you see a little picture of how they move around in that track, and then once in a while, or whenever you want, you can have in these gate zones that you see here, you can do 2-gate and single-gate operations on them. And actually, we are working on larger traps and having more qubits as we speak. More about that later. Then very recently there was this announcement of a joint paper together with Microsoft, where we demonstrated how reliable our qubits are and how much more reliable they become when you put error correction on them, when you make them logical, and sort of it becomes even 800 times better than when you don't do the correction. And then we also performed, and maybe this is more interesting, multiple rounds of syndrome extractions, one after the other. So this is a nice feat. And then actually yesterday there was another paper out, which maybe even nicer in some sense, which showed how to do the Fourier transform on, I think, 3 logical qubits, but doing it all in a fault-tolerant way, including sort of non-Clifford gates, which sort of in the previous result, they were only Clifford gates. And so maybe the take-home message for me and also for you is that this is really going much faster than I expected it to go. And this is a super interesting time to be working in this field of quantum computing. So I'm very happy that I can witness this. So now a little bit to my own talk. So the first quantum applications, as we all know, was Peter Shor, who did his cryptography, and then there was Bennett and Brassard and Eckert, who came up with quantum cryptography and quantum communication. Efficient quantum communication, and I guess you're all very familiar with these. First applications are simulation of nature and optimization problems. But I want to, and then there's also the algorithms that come out of quantum algorithms, but that are purely classical. So that's also something that came out of the field. And I want to focus for this talk not so much on computation, but more on communication, and in particular, some kind of cryptographic protocol that I've gotten very interested in. And so this is work that I did with a bunch of my students, and also some collaborators like Alex May and Wolfgang Löffler, who is an experimentalist in Leiden. And the idea is the following. So in 1969, we had the first moon landing, and this was a joyous event. Actually, I can still remember when I was a little kid, I can somehow vaguely remember this, I think. But then there are quite a few people who doubt that this actually ever happened, and that this really was a big hoax, and that it was all staged and filmed somewhere, I think in New Mexico. So this is a great lead-in to the problem that I've been working on, and that is how can you prove that you were at a specific location? And in this case, it would be fantastic if you could prove that these people were actually on the moon. Okay, so this is what position verification is about. It is the problem of proving that you are at a certain position in space. For example, it could be useful that you know that the launch missile command really comes from within the Pentagon and not somebody somewhere else is faking this. Or that you're talking to South Korea, not North Korea. Or maybe another one is the pizza delivery problem, where you try to play a prank on your neighbor by ordering 100 pizzas for that particular location. And then, of course, when the pizzas arrive, the neighbor doesn't know what happened. Well, if they had sort of position verification, they could verify where this order was coming from. And so this wouldn't work anymore. And more seriously, I think it's a building block for other cryptographic tasks like authentication, where now you don't use your key, a specific key for authentication, but you use your location. And so, for example, you can use it as a building block to have a protocol where you can decipher a message only when you are at a certain location, and not, and if you're not there, you can just simply not read what the message is. So position verification, let's dive into that, and I'm going to the one-dimensional case because that's sort of much easier, and it already harbors all of the problems that you will see in 3 dimensions, but basically everything I say will turn out to be true in 3 dimensions as well. So the problem is the following. I have 2 verifiers, verifier 0 and verifier 1, and a prover who sits in between these 2 verifiers, and he wants to prove that he is at a particular location, in this case the blue location. And this blue location, I mean, I chose it in the middle, but it could have been anywhere in between these 2, not necessarily where it is now. And we make some assumptions. We assume that the verifiers have coordinated together. Communication happens at the speed of light, no faster, but also no slower. Particularly the no slower is a real assumption. And furthermore, we also assume that computation doesn't take any time. And if it does, then sort of our results become approximate. But for now, bear with me and let's assume that we can communicate instantly and as fast as we want. And what do we want to prove? So this is the situation that an honest protocol should achieve. But we want to shield it from a cheating pair of provers, namely Alice and Bob, who claim that there is somebody at the blue location, but there isn't anyone. So they want to spoof the protocol that the verifiers think they have with someone at the blue location, but in reality, there's this Alice and Bob who try to fake this somebody at the location. So let's look at the first try, and this is called distance bounding. So time goes from top to bottom, and let's assume that verifier 0 sends a random message, a string of n bits, an x, to the prover, and the prover upon receiving that returns it. And now the verifier measures the time it took from sending to receiving back the exact same message, and this gives you an upper bound on where the prover sits. Right, it cannot sit further away than the return time to the verifier. And if you do that also from the other side, then in principle these two times should indicate exactly one location, and that's the location where the prover is. Now, let's look at how an attack would look like. Alice and Bob, well, they could intercept